Okay, we're good. All right, I am about to start, and let me share my screen. All right, and so for time's sake, I've already I just scanned all the work I did, and I'm not even gonna bother working out all the problems of like writing on the screen. I thought it would just be easier just to write it out. So that's what I'm gonna do because anyway, these problems anyways, I think are really easy. Like a lot of them are just like repeats from like the last worksheet, the homework. And then the ones that are new, it's just just a couple more equations you need to know. It's not that hard. But we'll start with any questions about the true and false? True and false, those also kind of repeats. So any questions here? I wouldn't think there are. No questions, I presume? No, right. I'm just gonna move on to the word problems then. Please. This is there. Okay. So we got these problems right here. Any questions about these 10, 11, or 12? Okay, no, I'm not muted. Is Zoom working? Just start at 10? Okay. So let me just read it out. A reaction known to generate 45,200 joules of heat causes the temperature of water in the bomb calorimeter to increase from 23.5 degrees Celsius to 56.8 degrees Celsius. What is the heat capacity of the calorimeter in kilojoules per degree Celsius? So basically this one, you just need to know the equation for heat capacity, which is just the heat of the known heat of a reaction over the change in temperature observed for that calorimeter. So that would just be 45,200 joules over the change in temperature, which is so it went from 56.8 to, or it went from 23.4 to 56.8. So I just did final minus initial to get 32.5. Then I end up with 1,390.76 joules. But I see in the answer or the word problem that wants it in kilojoules. So I'll just do the conversion factor and I got 1.39 kilojoules per degree Celsius. And so the closest one to that was B. And so I've already checked these and that's the answer. Any questions about that one? It's just knowing the equation for heat capacity. And then just making sure that you got all the variables to plug in. Are you good? All right. So 11 is just so let me read it out first. How much work is done on the system when the volume of the system decreases from 654 milliliters to 332 milliliters, assuming pressure of 1.10 atmospheres? So again, this is just a matter of knowing your equations. Just know the equation for work, which is equal to negative pressure times the change in volume. And so it gives me the pressure in the atmosphere. So that's our V, that's our P right there. Then the change in volume is this right here, 654 to 332. And so I just do final minus initial. So the initial or the final is 332, and then subtract that and minus 654, the initial. So I get a decrease in volume. And I just convert this to liters because the units that you want to use for work is always liters. And so I just plug that back into my original equation for work, and then I get 0.3542 liters times atmospheres. Note that this is not joules, but liters, but the units are liters times atmospheres, because after we calculate that, we just need to use the conversion factor for converting liters times atmospheres to joules, which is just 101.3 joules per liter times atmosphere. And so I just take that number times 101.3 and I get the final answer of 35.88 joules. And then it matches this one right here, B. Any questions about that one? It's just another memorize your equation kind of problem. Good. All right. So 12. So this so I'm gonna read it out again. Estimate the change in enthalpy of the reaction in kilojoules per mole for the decomposition reaction of this right here. So this is basically more or less the same kind of problem I did on the homework, except a lot simpler because there's only like there's as you can see, I wrote out like the homework did. I just drew it out. So like I got so there are two chlorine chlorine fluoride compounds right here. So I just drew two of those, and then I drew the arrow indicating the reaction. Then the reactant side, which just has a one F2 molecule and one Cl2 molecule. And so I just listed out. And so this kind of problem right here is deals with the enthalpies of bonds, because if you were to go back to the front, you could see that it gives you the bond energies of those particular compounds. You see the chlorine and fluorine, and the F2 and then the Cl2. So basically that's what we use for this part right here. And so I'm just gonna, and then for the equation that you need to know is the change in enthalpy of the reaction is equal to the sum of all the enthalpies of the bonds that are broken minus the sum of all the enthalpies of the bonds that are formed. And so basically your reactant side will be the bonds that represent all the bonds that are broken, and then the product side represents all the bonds that are formed. So in this case, there are two CLF bonds, and then they're broken, and then there are two of those. So that's why I wrote right here CLF, and then colon indicates that there are two of those kinds of bonds. And then the same thing on the reactant side, which is formed. And so there's a one F to F bond that's formed, and it's indicated by one, same with the chlorine. And so basically I rewrite it out as, so I'm going to rewrite the equation as change in enthalpy of the reaction is equal to 2 times the change in enthalpy of the bond enthalpy of chlorine to fluorine, because that's right here according to our equation, that's one of the bonds, that's the bond's broken. And since there are two of those, I will need to multiply the bond energy by 2, and then minus all the sum of the enthalpy of the bonds that are formed, which I got from the front as well. And then there are one of each of those, so I didn't need coefficients on those, and I got that in a huge bracket. And then I put subtract and then minus sign in front. And so if I just put this in the calculator, I get negative 13.6 kilojoules per mole, and that just matches C right here. Any questions about that one? It's pretty much the same thing as the homework. You good? Good. All right, I'm going to move on then. Okay. All right. 13. The standard change for the standard enthalpy change for the decomposition of silver nitrate according to the following reaction. This is change in enthalpy of the reaction 78.67 kilojoules per mole. What is the standard here formation of AgNO2 as in kilojoules per mole? So again, it's just a matter of whether you know the equation or not for these kinds of problems. And so so the equation is the change in enthalpy of the reaction is equal to the sum of the enthalpy of formation of the products minus the sum of all the enthalpy of formation of the reactants. And so I can rewrite it as this right here. So change in enthalpy of the reaction equals, and so one of the products is AgNO2, right? I'm going to start just annotate this. So this right here is one of the products. So I wrote it right here, the enthalpy of formation of AgNO2. Then I also got 1/2 O2 that's formed. And so I got that right here. But note that I also have 1/2 in front. That's because it was only like, if only 1/2 of O2 was formed, then only half of the energy was used to like create that. So that's why it's only one. So it's a 1/2 of that enthalpy, because there's only 1/2 created. And the same thing would apply if it was just like, instead of 1/2, it would be 2. So you multiply the enthalpy by 2 because 2 of them were created. But that's the general idea of why you want to pay attention for any coefficients that might be in front of the compounds in the chemical equation. And then so that's all the products, the change in the enthalpy of formation of the products, and I just move on to the reactants. And I can see that there's only one reactant, and that's this right here. So I just did minus the enthalpy of formation of AgNO3. But the question asks for AgNO2, the standard heat of formation of AgNO2. And so if I just do, and I see I got it right here in the equation that I wrote out. And so if I can just do a little bit of algebra right here, I can isolate this on one side, and then I can simply plug in the information to solve for the enthalpy of formation of AgNO2, which is this right here. And so I just, again, it gives it to you on the front page right here. Let's see, right here, see heats of formation, and it just gives it to you right here. So it's F2, there's O2, which is 0, AgNO3, which is negative 123.02. And so we go back over here. And so you can see where those numbers came from. So this would be for this right here. And then oxygen, the enthalpy of formation of oxygen is just 0. So that's why it's just 1/2 times 0. Then I got the enthalpy of the reaction, which is just given up here. And so I plug all those numbers in and I get negative 44.35 kilojoules per mole, which is this one right here. Any questions about this problem? Again, it's just kind of a repeat from homework, except a lot easier because there's a lot less compounds to deal with. Oh, flip the sign. So you mean like this portion right here? Let me red. This portion right here. Is that what you mean? That's just me. This is just algebra basically. It's just me moving all these terms right here to the other side right here. And so I could isolate this term right here, which is why I'm able to, so this side, see how is this isolated? Then I see, and then all the other terms have been moved over to these terms have moved to this side. And I just flip the equation around so it look a little nicer. Yeah, it's just algebra. That's all it is. Just be very careful about your signs because that will screw you up on the test. The negative 123.02. So that comes from this right here, the heat of formation of AgNO3. And so all I did was I looked back at the front to see what that would be, and that would be where is it? So heat of formation right here. And so I go down and I'm looking for the heat of formation of AgNO3, and I find it right here. And so the heat of the enthalpy of formation of that is just negative 123.02. That's where I got the numbers from. Basically, I had to go back up here to the front to look at these. So the kinds of problems that contain like heats of formation or bond energies, you'll usually want to go back to the front and look for like any of the givens because they basically more or less have to give them to you, or else you wouldn't be able to solve these problems. So that's where the negative 123.02 comes from. Then that's also where the 0 comes from. The enthalpy of formation of oxygen is just 0. Then this number here just comes from the problem itself right here. And that's basically where all the numbers come from. Does that answer your question? And more? Okay, good. Any other questions before I move on? Good. All right, so okay, this is probably the toughest one because I would assume that people wouldn't know how to do it because Paul Lindahl did a horrible job of teaching it, because the method I've got here is the method that the book taught me, and I think it's like a much better method than what Paul Lindahl was trying to teach us. So I'm just going to go ahead and walk y'all through it in case y'all aren't familiar with this method right here. So let me just read it. We're just gonna read this out right here. I'm sorry, I'm dissing on him. I told myself for like an hour trying to figure this kind of problem myself for like an hour. I'm like, bruh, I looked at the textbook and it took me like a minute to solve the problem. Okay, anyways, enough ranting. Question 14, calculate the standard enthalpy change for the reaction. This right here. Hydrogen gas plus bromine gas turns into hydrogen bromide gas in kilojoules per mole using the following data. So it gives us these equations here. It's kind of messy because the pencil's in the way. I'm sorry about that. So the first step in solving this kind of problem is you want to pick an equation that looks similar to the target equation. So I'm just going to go and circle the target equation. So that's what let me draw that. This right here is our target equation. That's what we want to end up with. And so we use these equations right here to get to that. And so, so that's what one is right here. So one is the equation I'm going to start with. So I'm going to look at these equations that it gives me right here, and I'm going to choose one that has a compound, has a matching compound in the target equation. And so the one I picked was this one right here, because I see that the HBr gas matches with this right here. The only difference is that they have a coefficient, but you don't have to worry about the coefficient for now, as long as these compounds match each other, the sign and everything, make sure they all match. And so that's why, so I just rewrote it down here. So this equation right here, I rewrote it right here. And so that's just H2 plus Br2 turns to 2HBr. And then the second step is to then choose some, okay, let me start over. So the second step is to start eliminating these compounds right here in exchange for what we actually want, which are these right here. And so that's what these equations, the given equations are for. And so in step one, yes, I could choose any one of these. It would, you would still end up with the same answer. But in this case, I just chose a 2HBr. It's the same process. Yeah. So in step one, I wanted to start with getting rid of the hydrogen gas right here. Because you see how it's hold on, so you see how it's H2 or H subscript 2, not let me erase all this. It's getting messy. So you see how it's H subscript 2, not just plain O, not just H, which doesn't have a subscript of 2. And so I'm going to look for an equation that involves H subscript 2 that and then see if that helps me in any way. And so I see that this equation right here has H subscript 2. And then I can see that I can exchange that for 2H. And so I can use this equation to cancel that, to remove this H subscript 2 right here. And so that's what I did. And so the rule is when you're trying to cancel out something, this in particular, this H2, the equation that you use has to have that same compound, but on the opposite side. So you can see right here that the H2s are on opposite sides right here. And so I'm able to cancel them out like that. And so, and then the equation that I use, you can see that the H2 is on the same side as the starting equation I chose. And so what I had to do was I had to swap the reactants and products. I had to swap the place where the reactants and products were. And then when you do that, you always have to do the same thing to the enthalpy. So kind of think of like math, whatever you do to one side, you do to the other. So it's the same concept here, except we're just dealing with enthalpy. So when you swap the products and reactants, you change the sign of the enthalpy. So in this case, originally it was this equation I used was at 436.4 kilojoules per mole. Then down here, you can see that I changed it to a negative because I swapped them around. And then also, I forgot to mention that I also have the starting enthalpy of the enthalpy of this reaction that I first chose right here. And so once you got this set up right here, you can then cancel out the H2s and then just do some addition. So I just add up these two equations right here. So we got 2H and we still have Br2 on the reactant side. And then we got just 2HBr on this side. And so that's what step 2 is. It's just the added equation. And then I add up the enthalpies right here. And I end up with a new enthalpy of negative 408.8 kilojoules per mole. And basically, I just keep repeating this kind of step, swapping, using equations to aren't we supposed to divide by two at first? Not necessarily, because right now it's if you were to divide by 2 right now, that would make it, you would still get the same answer, but it would make it a lot harder to do, because you can see that if you just kind of look at these equations right here, let me erase this stuff again. So even though this says 2 HBr and then this is only 1 HBr, which is true because you, in the end, you do want just 1 HBr. You look at the other ones and you see that, oh wait, did I? Oh wait, no, that's, well, I guess you, well, you could divide it by 1/2 at first, but then you divide everything else by 1/2. Or divide everything else by 2, then you'd be left with like these 1/2s. And then when you come to add these equations back to, when you add these equations together, you're going to be end up like dealing with fractions, and I didn't want to deal with that. So for now, all I focused on was just getting the coefficients right. And also because this H2 right here already matches the coefficient of H2 I had right here. So yeah, you see, so see how the H2 right here, the coefficient matches the one that's already given. So I didn't want to divide by 2 here because I didn't want to divide this by 1/2 2. I'd have to do that. Then I have to do the same thing for this one right here, which would have been annoying. So that's why I elected to not divide by 2 at the beginning. Sorry, I was kind of all over the place with that explanation, but that's why I didn't divide it by 2 at first. Does that make sense? And then at the end, I'll deal with the coefficients because it's a lot nicer work. And so, okay, got it. Okay. So then I got the second equation right here. And so I've got so hydrogen. So I got the hydrogen to match. It's just got a coefficient of 2, so but that's all right. And now the next thing I want to get rid of is Br subscript 2. So we go back up here, look for any equations, and I see this one right here matches. It's got Br2 in it. So then I want to get them on opposite sides. So I swap the sign. So I swap the swap this around, the products and reactants. And I also change the sign of this. So that'd be negative 192.5 kilojoules per mole. And then once they're swapped around, I can add them together to cancel out the Br2s like that. And then I just add them up together. So that's 2H in gas form, then 2Br in gas form. And so that's what this part's for. And then I'm just left with 2HBr right there. So I just bring that down right there. And then I add up the enthalpies right here, and I get a total of negative 701.3 kilojoules per mole. And then here, now that I've got all the elements to match, it's no longer H subscript 2, it's just H, which is what we want right here. It's right here. But the only thing that's off is the subscripts. So, and I can see that all of these have a coefficient of 2. And then the coefficients of this, the target equation is just 1. And so all I have to do is just divide this whole equation by 2. And then do the same thing for the enthalpy, because whatever you do for the equation, chemical equation, you have to do the same for the enthalpy. And then you end up with the target equation. And then after you divide this by 2, you end up with your answer. negative 350.65 kilojoules per mole. And as you can see, it doesn't match any of these, so the answer was none of the above. So I hope that method, excuse me, makes a lot more sense than the way he taught it. This is the textbook's way of doing it. Does anyone need any clarification about how I did this? It's basically, oh, yeah. I actually had second doubts. I thought it was this right here, but then I was like, it's gotta be none of the above. Like, because yeah, it is rarely ever none of the above. But in this case, I mean, now that I know the surefire method of finding the enthalpy, I know that it could not be this right here because I was keeping track of the signs, because you want to keep track of those signs. Those signs are very important. But yeah. Does anyone have any questions about this? It's so basically, if I had to sum this up, it would be basically adding up systems of equations. And you're just looking to like cancel terms out. That's all you're trying to do. I'm gonna go ahead and clear all this. Any questions? You don't have any questions? Anyone? All right. Oh, you got one? Yep, give it to me. Can you do a bomb calorimeter problem? Well, you mean like the one from the notes you're saying, or like the one that we did earlier? Because like where was it? This one? Okay, I see. Thing is, I don't know any more bomb calorimeter problems. I would if I did know any more. Or I could just steal the one from the notes, basically. But it's let me, why did it zoom in? Let me look at my notes real quick. Yeah, I'm reading like the one that's like the cookie weighs 7.25 grams using the same calorimeter as before. Yeah, give me a minute. Okay, I am a bit curious about that. Let me actually look that up real quick, that bomb calorimeter one. I don't think I'll like go through it exactly. I'm just probably just gonna read it through. Like, here's notes. What what day was this? This is probably the last thing I'm gonna be going over because I'm running a little short on time today. Sorry. Day 10, November 10th. See right here. Copy cut. Okay. Um, Not so sure how to exactly go over this. Honestly, I couldn't really help you with this kind of problem, but other than just like reading the notes and seeing how it's done. I don't think it's fairly too complex. Just I think it would just be a matter of knowing the equations and knowing the info, and then doing any other substitutions if you need to with other equations. But yeah, I don't think there's much I could do for you in that sense. Yeah, sorry about that, if that's all right with you. Yeah, but as long as you understand everything else, you should still get a pretty good score on the exam. That's just I'm gonna hope that there's not a very complex bomb calorimetry calimo how do you pronounce this word? Calor calorimetry? Bomb calorimetry. I can't pronounce it. I literally cannot pronounce this word and it frustrates me so. Calor calorimetry. Calorimetry? But that's an O in the middle. Oh yeah, I'm getting off topic now. But calorimet calorimetry. Calorimetry. Okay. That still sounds like really weird word to me, so I'm just okay. Well, um does that, but besides the this question right here, does anyone else have any questions about the practice exam? I'm just gonna head back over there. Any questions about this stuff? True and false real quick? Sure, I can do that real quick. So okay, one, true or false, the change in internal energy of a system equals the work done in the system plus the heat gained by the system. So this is just whether, this is really just a question of whether you know the equation for internal energy, which is just change in internal energy is equal to Q plus W. So this is true. Two, at constant pressure, the overall enthalpy change of reaction is this right here, and that is false because let me see. So the enthalpy, the reaction is change in enthalpy is equal to change in U plus P times delta V. And so so why is it? Yeah, pretty much. Yeah, just go over the slides and you should be fine. Pretty much, just memorize a few things. I'm actually not exactly sure why. I just had a feeling it was false because there's also internal energy in the equation. So like I think that's why it might be wrong, because it's not just this right here, it's also internal energy. So that's why I think it's false. That's that one. And then for the or three, standard state is when the temperature, pressure of gases and concentrations of a species in the solution is divided to be 25 degrees Celsius, 1 bar and 1 M. That's just pretty much memorization. That's true. True or false, the change in internal energy of a system is equal to this. Well, we have never seen an equation like this before, and this is most definitely false right here. There's no such thing as like internal energy initial and internal energy final, so that's false. Enthalpy of a system is this right here, is that's true also. According to the notes, 6, the internal energy of a chemical system equals the sum of the kinetic and potential energy associated with each component of the system. So this is just thermodynamics right here, like, you know, so you can kind of imagine it instead of like a chemical system, like you're on a roller coaster. It's like, you know, at the very top, you've got all the potential, all your energy is potential energy. Then as you start going down, some of that potential energy is converted to kinetic, but some of that energy is also still potential because technically you're still you still have height. And so that's what, so you have potential and kinetic energy at that point, but the sum of those potential and kinetic energies at that point would equal the total amount of potential energy you would have at the very top when you were standing still. And so this is true no matter where you are on the coaster. And so this would be true. That's just a little analogy I use to memorize that. And so that's that one right there. And then I move on to the last few. True or false, a reaction performed at constant pressure cannot do work on the surroundings. Again, just know your equation. You can see that pressure doesn't matter what pressure it is, as long as pressure is not 0, you know, but as long as pressure is some number, then there will be work. It's when it's there's no change in volume is when there's no work done. So this is false. And Hess's law states that heat can neither be created nor destroyed. Again, just something that you got to memorize. Just know the definition of Hess's law. And then 9, true or false, the first law of thermodynamics requires that heat lost by the system must be gained by the surroundings, which is true. It's just the first law of thermodynamics. And yeah, that's pretty much all the true and false. Just study your notes. That's it, and memorize. It's not that bad, honestly. But any questions about that? The true or false? You good? We all good here? All right. I hope y'all will. So I'm going to go ahead and end it here. You know, that's all right with y'all. And I'm going to, of course, upload this to the GroupMe. So if y'all have any questions, y'all can come back to this. And for the other people in the GroupMe chat. And yep. And good night, everyone, and good luck on your exam tomorrow. And I will see y'all tomorrow. Yes, you will all get 100s. I believe in all of y'all. Yep. All right. Goodbye, y'all, and have a good night.